Okay guys, so we are continuing part 6 of the linear system theory. So we got that E matrix exponential EAT we derived together, which is a Laplace inverse of, for refreshing your mind, SI minus A, matrix A inverse. And also we saw that we can calculate that by using that Sylvester interpolation method. If you remember that we had this determinant to calculate that. It is 1 lambda 1 square and lambda 1 m minus 1, that's right, and E lambda 1 t, and then 1 lambda 2 square lambda 2 m minus 1 E lambda 2 t, and continues for 1 lambda m squared, that's right, lambda m minus 1, and E lambda m t, that's right. And the last line is I identity matrix A squared and A to the power of m minus 1 and E A t. And I did example on part 5, and you saw that how I calculated the matrix exponential. Here we go. Right? So and the lambda 1 and lambda m, lambda 1 to lambda m, they are matrix A eigenvalues. Okay, so you can calculate the matrix exponential from this or from this. Understand? So, for example, I did example just refreshing mind. If you have a 3 by 3 matrix or third order system, 1, 2, let me do this, 0, 0, 0, say minus 2, 0, 0, 0, 3. So the third order system, so you have 3 by 3 A matrix, where that x dot is equal to, we are talking about the LTI systems, that's right, and the BU, that's right, and this is a CISO system that we are talking about. So you have to first calculate eigenvalues, that is lambda I minus A is 0. And if you do that, simply because this matrix is diagonal, that's right, so you can say lambda 1 is minus 1, lambda 2 is 2, and lambda 3 is minus 3. This is the trivial rules in the algebra, that's right, linear algebra. So by having this, now you can make this Sylvester thing. So how many eigenvalues we have? 3. So you're gonna have 1 lambda 1 and m minus 1. You have 3 m minus 1, 3 minus 1 is 2. So it's gonna lambda 1 square and E lambda 1 t. Again, because we have 3 eigenvalues, 3 lambdas, so the highest order here is going to be lambda 1 m minus 1, 3 minus 1, going to be 2 squared, that's right. And now 1 lambda 2 is squared, E lambda 2 and t, and 1 lambda 3 is squared, because you have 3 eigenvalues, E lambda 3 and t, and I A square E A t, that you want to calculate this. And as I did in part 5, you have to expand this, and you can get the unknown, that is the matrix exponential of this. Understand? So we are until this point, and also I said that I said that the solution of this using the Laplace inverse was this. Remember, x of t, if you remember, you got your notes, is matrix exponential that we can calculate by this or by this. State variable at time 0 plus integration from 0 to t ea t minus tau matrix B, this matrix u of tau, that's right, and d tau, that's right. And I did example on part 5. So now let us continue our topics. So having these until from chapter 1 to chapter 5 for refreshing your part 1 to part 5 of the YouTube links. Now I'm talking about clay. Hold on, I have to change this. Okay, so where we are? Clay. Oh, what the? So it is K Hamilton theorem. You have to know this theorem, right? This is very important. Oops, hold on guys. Okay, so theorem. So it says simply, let me change the color. It says that matrix A satisfies its own characteristic equation. So what is characteristic equation? Means that eigenvalue equation, right? Remember in the previous example, this was the matrix X, that's right, a given matrix, the square matrix. So when we wanted to calculate the eigenvalues, use these relations, right? So I'm just writing here, guys. So A is, get here, 1 0 0 0 2 0 whatever minus 3 for simplicity, right? So this eigenvalue characteristic equation, the name of this characteristic equation is lambda I again minus A, that's right, which is this identity matrix lambda minus 1 0 0 0 lambda minus 2 0 0 0 and lambda minus 3, right? So simply because this is diagonal matrix, so its determinant gonna be lambda minus 1 in lambda minus 2 in lambda minus 3, that's right. You can write as a lambda square minus 3 lambda plus 2, that's right, and lambda minus 3. Why I'm doing that? Because I have an intention to teach you a point. So what you get is a lambda 3 minus 3 lambda 2 minus 3 lambda square plus 2 lambda and minus 3 lambda square, that's right, plus 9 lambda minus 6. So finally what you get is this lambda cube, this with this is minus 6 lambda square, this with this gonna be 11 lambda minus 6, and this is the final result. So this is characteristic equation, that's right? Right? Or eigenvalue polynomial, that's right? Understand? So from this we can solve for the eigenvalues. But we know from the beginning that is 1 or 2, 3. So why I'm writing this? Because I want to tell you that the eigenvalue problem or characteristic equation, other name, is the general formula for n by n matrix. Lambda n here was 3, so gonna be lambda 3. That's right, the highest value. Lambda n plus a1, lambda n minus 1 here was 2, plus a2, lambda n minus 2 here was 1. That's right. And finally a n minus 1 lambda plus a n is 0. This is what? Eigenvalue problem or characteristic equation. That's right. So this Hamilton theorem says that any given n by n matrix satisfies its own characteristic equation. Means that you can write this. I'm changing the color. Here we go. an plus a1 lambda a n minus 1 plus a2 and a n minus 2 plus a n minus 1 a plus a n what? You cannot leave it as 1 because you are dealing with matrix here. Gonna be I is 0. So any square matrix satisfies, I'm talking about the LTI systems, satisfies its own characteristic equation. That's right. On the other hand, let me double check this. 3 lambda plus 2, so it's gonna be lambda cube minus 3 lambda square plus 2 lambda minus 3 lambda square plus 9 lambda minus 6. So it's gonna lambda cube minus 6 lambda square plus 11 lambda minus 6. So on the other hand, for this example, you can say a cube minus 6 a square plus 11a minus 6i is 0. No doubt, which it is. Go on MATLAB, right? No doubt that that is valid. Understand? So we can find this proof in your book. I just skipped that, okay? So it's sort of ridiculous that I do that. Just killing your time. This proof can be found in your book, okay? So, but you have to know about the theorem. Now, hold on. Now, the question is that I told you you can name eigenvalue equation as characteristic equation. So it has a reason, guys. So this backs to undergraduate control. How? Remember, let me refresh your mind. This was a transfer function, that's right, y over x from undergraduate control. That can be, I don't know, b naught sm plus b1 sm minus 1 and finally bm, that's right, and say sn plus a naught sn minus 1 plus finally an, that's right, an. Remember that in undergraduate control, okay, we were calling this this equation what? Can you tell me? Yes, characteristic equation. So characteristic equation is a quotient that gives you the system what? System what's undergraduate control? The system poles. The roots of this denominator was the system zeros, if you remember. That's right. But here it gives you the system poles. So that's why we name it characteristic equation. Why we name it? Because this is the internal dynamics of the system. That's right. This is the internal dynamics of the system. We want to see how the system behaves by itself. This is undergraduate control. Okay. So why now we are calling the eigenvalue problem in state space characteristic equation? Well, look at here. X dot, as I did previously, is equal to AX plus BU, right? Yes, this is LTI system, linear time invariant system, LTI system. That's right. If you remember that I was trying to find the solution of that, I applied what? I applied Laplace to the both sides, Laplace transform. So it was x of s minus x at time 0. These are the state variables. Is a x of s plus bu. Remember? So I removed this term to the left hand side. So we had x of s si, you cannot leave as 1 because you are dealing with the matrix, minus a is equal to, and moving this to the right hand side. So x at time 0 plus plus b u of s, remember? And now, because the thing that we want to solve is what? Is the state variables. So we multiply the both sides by si minus a inverse. That's right. So you said x of s is equal to x at time 0 si minus a inverse plus b u of s minus a inverse. So I'm gonna just, guys, I wanna do this si minus a inverse in x at time 0 plus b u of s, right? Understand? But we know from high school that the matrix as A inverse gonna be adjugate of that matrix divided by what is determinant. That's right. This is high school topic in linear algebra. So now the inverse of this is what? Inverse of Si, as I taught you in the matrix exponential, is again adjugate of this divided by determinant of that, right? So on the other hand, x of s, I'm just writing in symbol form, si minus a adjugate divided by si minus a determinant in at time 0 plus b u of s. I'm just skipping here. I taught you in undergraduate control the denominator that we were naming as characteristic quotient gives you the poles of the system. And we saw here that this finally ends to what? This equation, that's right. Si minus a, this eigenvalue problem. Look at here, guys. What do you see here? Oops, the characteristic equation. Exactly like this. If you have n by n matrix, you're going to have the polynomial as I did here. That's right. As I did here. You're going to have what? Sn plus a not Sn minus 1. So that's why this the eigenvalue problem gives you the characteristic equation. Bingo. As we had in undergraduate control. This is very important and simple. That's right. That's why when we are talking about the pole placement later in this course, we are talking about the these kind of things, characteristic equation. So just to clarify why I said that, okay? Now, after knowing that the Hamilton theorem, I have to refresh your mind about two concepts: linear and independent dependent vectors, linearly dependent linear dependent and linear independent vectors, or matrices. Oh, hold on, guys. Okay, hope that works out. So we have to appreciate all of the pandemic. Matrices. Okay. So we say, this is definition, a n by n matrix is non-singular if its determinant is not 0, or its, let me change the color because you have to define it, its rank is n. N by n matrix is n. Okay. So if that happens, we say n columns or row vectors of matrix A are linearly independent. Okay, so if a matrix, if it is non-singular, means its determinant is not 0, its rank is n. Okay, its rank is n. So suppose, so now, but I'm pretty sure that you know about the linearly independent vectors, right? So suppose you have this vector, guys. You have this vector, a naught x1 plus a1 x1, a2 x2, and plus a3 x3 plus an xn is 0. Okay, an xn is 0. This vector is linearly independent if, for this equality to 0, all a1, a2, and until an, none of them are 0. If none of them are 0, so this vector means linearly independent. Okay, so it is linearly dependent simply if at least one of the eyes are 0. That's right. Let me give an example, guys. Suppose that, oh, what happened? Suppose that x1 is this vector, guys. 1, 2, 3. And the x2 is 1, 0, minus 1. That's right. And the x3 is this vector. 2, 2, and 4. Now let us consider this a1 x1 plus a2 x2 plus a3 x3 is 0. We want to hold this equality. That's right. So we have to find a1, a2, and a3. So you see that this equality is not possible. This equality is not possible until that guys, I think that I said reversely. I'm getting older, guys. So it's linear independent if all of them are 0. Okay, if all of them are 0. If one of them is not 0, it's linear independent. That's right. And let me change this to +1. So you see that so you see that we want to examine a1, a2, and 3 to hold this equality. That's right. But it's very clear here, guys, that let me change the color, that x3 minus x1 is equal to x2. 2 minus 1 is 1, 2 minus 2 is 0, 4 minus 3 is 1. So you find the relation between them. x3 minus x1 is x2. Or on the other hand, you can say here x2 plus x1 minus x3 is 0. That's right. So you see that not only one of the i's here, 3 of the i's are non-zero. So these vectors are linearly dependent vectors. Understand? So these vectors are linearly dependent vectors. Clear? Understand? Because there is a correlation between the vectors. See that relation here? Understand? So if I make a matrix by these vectors, look at here, 1, 2, 3, put x1 here, 1, 0, 1 here, and 2 and 2 and 4 here. If I calculated its matrix, I bet that it must be 0. Please do it at home, because this is linearly dependent systems. Understand? So for the example, there is a linear relation between linear dependency between this column, and this column. What is that relation? We just derived. This is the relation. Understand? So that's why in the high school the teacher says us that if you see, suppose you have a matrix like this, a1, a2, a3, a4, a5, a6, a7, a8, a9. So look at the columns or the rows, it doesn't matter. Okay, I'm talking about the columns. We say if a row or column is a multiplication of another, no doubt that its determinant is 0, and we say that this matrix is singular, and this is singular matrix, the determinant is 0. For example, look at here, guys. If you have 1, 2, 1, 5, 3, 2, and 2, 4, 1. What do you think about the determinant of this matrix, guys? The determinant of this matrix, without calculation, obviously 0. No doubt it is 0. Let me do that for you. It's gonna be this 3, 4, 2, 1, gonna be minus 5 in 2, 4, 1, 1, plus 2 in 2, 3, 1, 2. 3 minus 8 minus 5. 2 minus 4 minus 2 plus 10 plus 4 3, 4, 1 minus 1, 2, 4, 1, 1, 2, 2, 3, 1, 2. So it's going to be 3 minus 8 minus 5, 2 minus 4 minus 2 plus 10, and 4 minus 3, 1 plus 2. Oh, what happened? Hold on. Oops, I'm stupid. I multiplied this must be 2. I multiplied by 2. So this 3, 4, this is going to be 2. So, and 6 minus, this is 2. Okay. This is 2. And 5, 2, 4, 1, 2 again. This is going to be 0. And this is going to be 1, 5. I'm getting older. 2, what were 2, 2, 3, 4, 2, 2, minus 5, 2, 4, 1, 2, 2, 4 minus this. Why it doesn't go to 0? This is when you teach too much, that's the result from your brain. Hold on. Oh, this is a trivial mistake. 6 minus 8 is minus 2. So it's gonna be 2 is 0, obviously. That's right. Sometimes you have glitch in your brain, like me. So why this happened? Because if you look at the columns of this column is 2 times of these columns, right? This column is 2 times of this. So there's a linear relation between this column and this column. Obviously 0. And another rule is that if you have this matrix 1 minus 0.5, 3, say 0, 0, 0, 1, 2, 3. What is its determinant? Obviously 0. Why? Because if you write a relation between this row and this row and this row, the coefficient of this second row can be non-zero. Look at here, can be non-zero. That's right. For example, if I say a1, okay, a1 x1 plus a2 x2 is 0. Look at here, I'm saying this as x1, this row I'm saying as x2. That's right. So I say transpose, I'm just making transpose. It's gonna be a1 2 minus 0.5 3 plus a2 transpose of this 0, 0, 0. To have this equality, that's right, you can say, obviously you can say a2 can be any number, a2 can be 5, but a1 must be 0. That's right. So one of the coefficients are not 0. So the rows of this column, they are linearly dependent, and that's why its matrix is 0. Understand? So, and we are done with this. Now, okay, I thought of non-singular and independent. Independent is singular. And now next topic is singular. Now you know it. So now the singular. Singular is this. Hold on, guys. Okay, we got that. So we say n by n matrix is singular if its determinant is 0, as the previous example, or its rank is less than n. So in non-singular, rank is n, but here for the singular matrix is less than n. Okay, so or its column, as I showed to you, or row are linearly dependent this time. Dependent. That I introduced to you. See here, dependency and independency. Understand? So now let me focus on one thing. What is rank? Rank of a matrix. What is rank? Rank of a matrix is simply number of column or number of linearly independent column or rows of that matrix. Okay, this is very important, guys. Rank of a matrix. Suppose for this matrix that is 1, 1, 0, 0.5 and 10, no doubt that the rank of this, oh, what happened? No doubt that the rank of this matrix, rank of matrix A is 2. Why? Because its determinant is 10, non-zero, and the columns or the rows of this matrix, they are linearly independent. So you have 2 rows or 2 columns of this matrix that they are linearly, actually this matrix, specific matrix, let me write about the column. So A1, I'm saying A1 1.5 plus A2 0 and 10. So if you want to have this equality, that's right, so if you want to have this equality, so which A1 and A2 you're going to select? Which A1 and A2? Only you have to say A1 is equal to A2 is equal to 0. only thing that you can have. That's right. Understand? So this is the rank of the A. So now if you go to the MATLAB, it's very easy, guys. You don't have to calculate by the determinant of the matrix. If you go to MATLAB, let me run the MATLAB. And yeah, and it comes up. So because based on definition of linearly independent matrices, so look at here, is linearly independent if all the coefficients must be 0, and which are. So this matrix columns or the rows are linearly independent. So its determinant is 10 is not 0, and its rank is, because this is 2 by 2, its rank is 2. Look at here. So let me type it in here. Suppose you have matrix A, as we had here is 1, 0, and the next line was 0.5 and 10. That's right. So simply you type rank, as we say, rank of A is 2. So because this 2 is full rank, so determinant of the A is non-zero value, 10. That's right. So another. So suppose A is equal to 1, 2, 3, 2, 4, 6, minus 10, 0, 100. So what to expect about this matrix, guys? I say the rank of this matrix is maximum is 2. Rank of this matrix is not 3. This is 3 by 3. Why it is 2? Why it is not full rank? Because the second row is the double of the first row. So there is a linear dependency between the rows of this matrix. Obviously, if I calculate the matrix determinant, it's going to be 0. So this is singular. Understand? It's very easy. So we did about these definitions until we continue by the next class. Okay? Here we go.